Dear friends, a very happy morning to all. On behalf of Francis Xavier Engineering College, I would like to extend a very warm welcome to every one of you who is watching this webinar. We thank you all for taking time out of your schedule and joining us with this event. I am Ram Kumar, Assistant Professor in the Department of Mechanical Engineering. It is a great pleasure in sharing a few words about our college and our department. Francis Xavier Engineering College is located at Tirunelveli city and it was established in the year 2000. FX Engineering College comes under the SCAD group of institutions and our institution has been offered autonomous status in the year 2019. We offer 6 UG programs, 10 PG programs and research centers. Our college has achieved many awards. Among all, I would like to list a few to your knowledge. We got Gold category for Industry Linked Technical Institute, which was awarded by AICTE CII survey. In Chronicle Engineering College survey, we achieved 3rd position among 19 engineering colleges in India. In Times Best Engineering College survey, our college has achieved 15th rank in Tamil Nadu and 108th rank in India. Apart from all, we got ICT Academy, Tamil Nadu Academic Partner Excellence Award in the year 2017. Regarding the Department of Mechanical Engineering, it is the largest department on the campus with 600 plus students, 30 plus faculty members and with good infrastructure facilities. We offer BE in Mechanical Engineering and ME in Industry Safety Engineering. The UG program is accredited by the National Board of Accreditation. We have FANUC Center of Excellence for CNC Center, BMW and Hyundai supported mechanical labs. Our department has signed many MOU with the leading manufacturing and service industries. Apart from regular academic activities, our students have been trained and imparted with various skill training programs and value-added courses. Our students are actively participating in many technical competitions, winning prizes and add glories to our department. We also offer international certified program on computer-aided design and non-destructive testings. We have also organized many international conferences, workshops and funded seminars. Today, we are organizing this online webinar. I hope the session will be more useful for all of us. On the final note, I welcome all the viewers for the session and hope we will have a productive time. Thank you all.
Hello everyone, this is Maheshwari, Assistant Professor in the Department of Mechanical Engineering, Francis Xavier Engineering College, Tirunelveli. It's my great privilege to introduce our resource person, Dr. V.N. Jagannathan, Assistant Professor in the Department of Energy and Environment, National Institute of Technology, Tiruchirappalli. He completed his undergraduate in Mechanical Engineering from Anna University, Chennai in the year 2006. He completed M.Tech in Energy Engineering from CEG Campus, Chennai in the year 2009. In 2019, he completed his PhD from IIT Madras in the title of syngas synthesis using biomass gasification with O2CO2 and O2 steam mixers. After PG, he worked with renewable and conventional power plant technologies and he get the 1.5 years of teaching experience. After PhD, he was working as PDF at IIT Madras. He published 5 international journals from his PhD topic. He won TCS Innovation Award of 2019. I welcome you all for this session. I wish you a great learning. Thank you everyone. And over to the speaker, Dr. Jagannathan.
Good morning, one and all over here. My name is Jagannathan. I am assistant professor from NIT Trichy, and I'm going to start this session on biomass gasification. What are the facts and what are the future research area which we can work with this particular problem? I'm going to just share my experience and my research experience and what is a thing which has been read about biomass classification for so far. I just want to summarize what is there, what is need not to be done, and what are the future directions of research. That is going to be this webinar is all about. So let's go into this presentation. Yeah, so this is the brief of the presentation. So we have an introduction, some interesting facts on biomass thermochemical conversion, new findings, that is the experiments done by me and the results and discussion of my experiments and some theoretical results, and the overview of the biomass gasification and further future directions. So this is what the seminar is going to be all about. Now we have biomass is going to be one of the renewable energy. You all very well know that. So what are the important points about biomass system? So that is what you are going to see now. So biomass is going to be a only above ground available renewable energy, which is an hydrocarbon or carbon source. So this is a very important point. Why biomass is actually distinct from other renewable energy technologies. So only from biomass, it is actually made up of hydrocarbons. So this hydrocarbons actually, this is a kind of renewable source. So what I mean is, whatever the carbon dioxide which is being let out by the plants, it is going to be absorbed by itself during its growth process. So we, in overall perspective, the net CO2 emissions to the atmosphere is going to be zero. So that's why it is called as a carbon neutral fuel. And this is the only fuel which is actually having hydrocarbon or carbon, which is actually renewable source. That is one important point about biomass. The next is almost India is going to be an agricultural country, so we know that, and almost like 500 million metric tons of agro residue waste as forest waste, this has been included here, is going to be generated per annum. So out of this, basically, since we are actually based on agro-residue country, we generally have an habit of using the biomass for cooking purposes or some household purposes or some other, say, some small-scale industries or some large-scale industry, for example, biogas cogeneration. So these kind of plants actually use some biomass already which is available. Okay, so out of this, if we just take the fraction, almost like 120 million metric tons is actually generally considered as agro waste, and it is generally burnt in field. So this we know. Because of this, there is a lot of pollution which has been created. We have been reading in newspapers about the pollution which has been taken in northern parts of India. All this is because of the burning of the biomass in the fields itself. So what I'm trying to say is, there is a considerable amount of biomass which is available, which is actually a kind of waste, okay, which is generally burnt without used for any useful purposes. And then, so other than power and heating applications, the one important thing is about biomass is it can be used for generating fuels, chemicals, and some value-added products like activated carbon, biochar. There are a lot of value-added products also can be produced with biomass, since this is a hydrocarbon source. Okay. So I'm just showing some examples of agro residues, forest residues, just for your reference. Now, based on the biomass types and what are the techniques it can be characterized. So that is the next slide is all about. Biomass is generally, there are many definitions for biomass. So the general definition which I would like to say here is, biomass is a plant and animal matter derived, which is generally derived from recently living organisms. That is a definition which I will go about here. And basically this biomass is going to be classified into mainly two categories, that is dry biomass and wet biomass. And when we say wet biomass is going to be a kind of biomass is available, like for example poultry litter, or say for example cow dung, or say example vegetable waste, food waste, all those kind of things which is actually having a moisture content very high. For example, more than 30 or 40% is going to be falling under this category of wet biomass. Okay, which is actually biodegradable. That is one more added thing over here. So this wet biomass, this can be gone to anaerobic digestion. You know this biogas plant, and you know this process, anaerobic digestion, biomethanization it is called. And we can produce two products mainly. One is going to be fuel, and next is going to be manure. And the next category is going to be dry biomass. In this dry biomass, what is dry biomass? Dry biomass, I mean by biomass which is actually having a moisture content lesser than or equal to 30%. That's what I call as dry biomass here. So this is generally given two different techniques are being used. One is thermochemical techniques, and another is actually physiochemical techniques. For example, seeds of plants. For example, jatropha seeds, or if you, in that case, if you say coconut or vegetable oil, which is derived from any plants. For example, coconut oil. This is actually subjected to transesterification process to produce biodiesel and glycerol as a byproduct. And this is a well-known technology. Most of you will be knowing about this. And this is one of the route also. The next route is going to be thermochemical conversion. This thermochemical conversion is majorly divided into three types. One is combustion, or next is gasification, and next is pyrolysis. So as the name implies, thermochemical conversion. So thermochemical conversion means we are actually subjected the biomass to thermal chemical reaction with an application of heat. So what we do is, first is combustion. Combustion is nothing but burning the biomass completely. That is stoichiometric combustion or lean combustion, whatever we call. So again, this is in combustion, we burn the biomass completely. And so since we burn the biomass completely, the product what we get is generally heat or power. Heat or power is going to be generally the product. Heat and power is generally the product. And if you take gasification, gasification can be defined as a substoichiometric conversion, or that is not the right way to put it actually. It is a staged conversion, gasification or staged oxidation reduction reactions. So for that to get a desired gas as an output, and also we can get other things also through this. I will discuss more about this in detail. So the mainly what I'm saying is we can get fuels out of here, and we can actually get chemicals out of here, and we can generate power also here, and we can actually use this for thermal applications also. So this has 4 applications: fuel, thermal, power applications, and chemicals generation. The next type is going to be pyrolysis. The pyrolysis is, again, this is also thermochemical degradation, thermal degradation of biomass, we can say. So in absence or in a very little presence of oxidizer. The oxidizer can be either it can be air, or it can be another combinations of oxygen, CO2, or oxygen steam mixtures, whatever it is. So this can be done, pyrolysis can be done in the absence of oxidizer, or it can be done with a little presence of oxidizer also. So the main product here is going to be mainly heat, charcoal again, and then we can also have bio oil. Okay. The next is going to be, so these are the different 3 types of thermochemical conversions here. And next we are going to see about how are we can categorize the biofuels, which is generally got out of this biomass, into 2 different types. That is going to be first generation biofuels and second generation biofuels. So what is first generation biofuels? So first generation biofuels are, which are the biomass, the biofuels which is derived from food crops and feeds. Okay, for example, we can say bioethanol production from starch crops, or say for example biodiesel production from sunflower oil or coconut oil, for example, that reason, via transesterification. So this is the type. So main drawback of this first generation biofuels are, this may affect the food chain. So this is not generally preferred for used as a biofuels. So there are major constraints. There are major resistance from people of using first generation biofuels as a source. The next is going to be second generation biofuels. This is generally meant for using non-food crops. For example, say Jatropha sarcas. That is a non-edible oil. Okay, we can use that. Or say for example, syngas, which is derived from rice husk, which is otherwise is going to be waste, which is generally going to be burnt in fields. So that is going to be used via here to produce syngas via gasification. This is one of the second generation biofuel. And also we can have biogas from kitchen waste via biomethane. This is also one of the examples for second generation biofuel. So second generation biofuels means we don't affect the food chain. And this is going to be used, this is going to be available in surplus, and it is considered to be as waste. And since it is going to be a waste, it is generally burnt, and it is giving undesired effects like pollutants and everything. So to avoid that, we are using this for energy purposes. So that is the main objective of second generation biofuels. So this is the most preferred form of fuels. Now coming to the biomass. Biomass majorly, I will just discuss about what is a biomass is all about. Biomass is majorly I am talking about lignocellulosic biomass here, to be very clear. So lignocellulosic biomass, what I mean here is which is derived from plant material. That is a dry biomass category here. Majorly this lignocellulosic biomass is consisting of 3 main components. One is going to be cellulose, next is hemicellulose, and next is lignin. Okay, this is the typical weight percentage. This will vary from biomass to biomass, doesn't matter. Now it will also have extra, for example, crude proteins, oil extraction, ash. Ash may be very less for certain biomass. For example, wood is having very less ash content, whereas if you take rices, it will be having more ash content, more than 20-30%. Whereas crude proteins and all will be more available in, for example, in coconut shell or some cashew nut shell kind of biomass. It will be more. For other biomass, it will be very less in category. Generally, it will be less than 5%. For some biomass, it will be higher also. So, when we generally take any biomass with on the basis of dry and ash-free basis, the chemical composition, that is the carbon content, hydrogen content, and oxygen content of any biomass is going to be universally almost same. Okay, almost same. This ash content and moisture content may vary. Okay. So generally the cellulose and hemicellulose, if we just put together and we actually try to calculate the ultimate analysis, there is the empirical formula of the biomass. It is generally turned out to be CH1.6 and O.9. This is almost a good approximation, and this may vary for certain type of biomass. Doesn't matter; it will not change very widely. Okay. So based on this ultimate analysis, if we have stoichiometric conversion, for this to get completely combusted, we require almost 4.5 grams per gram of air per gram of biomass. So that is the stoichiometric S value. Okay. So now, if we take the ultimate, there is a typing error here. This is approximate analysis. If we take the approximate analysis, we have moisture, volatile matter, fixed carbon, and ash content. So moisture will be generally less than 30%. That's what I defined as dry biomass or lignocellulosic biomass over here. Volatile matter will be generally between 40 to 80, and fixed carbon will be from 10 to 30, and ash will be from 0 to 40%. This is a typical numbers. This may vary for biomass to biomass. So generally, if you say most cellulose, hemicellulose form volatile matter. This cellulose and hemicellulose forms volatile matter in a biomass. That is this, and almost the remaining lignin and ash will form char, which is almost 20% of by weight. So 80% will be volatile matter and 20% will be fixed carbon. The remaining will be moisture and ash, which is I am reporting here on dry and ash-free basis. So 80% will be volatile matter and 20% will be char, a rough number. So for it to get completely, the volatiles are nothing but hydrocarbons, which will actually evaporate at lower temperatures. So that will be 60% of the stoichiometric requirement is going to be used for complete combustion of volatiles, as well as the remaining 40% will be used for char oxidation. So this is the number. So generally, whenever we are operating 60 stoichiometric, almost like lesser than 60% of the stoichiometric air requirement for any particular biomass, that is going to be gasification. If you are going above that regime, that is going to be char oxidation regime. So this is very important thing to follow. So 60% lesser than S, 60% of S, we can say that is gasification. If you go more than 60% of S, that is remaining 40% also, if you start to supply, then it is going to be, char is going to be not available for reduction reactions. It is going to be available for oxidation reactions. I'll explain about what is actually happening in our gasifier in a few slides after this. That will be very clear. Now you just remember this number. This 60% of S is called as volatile stoichiometry. The volatile stoichiometry means the stoichiometric amount of air required for complete combustion of volatile hydrocarbons. So that is called as volatile stoichiometry. That is denoted by phi V here. Okay. Now let us go to different types of gasifiers. So generally we have been heard about these terms, like we have been studied this lot of things. We have three main classifications, or two main classifications we can say: fixed bed and fluidized bed. In fixed bed, we do have systems like updraft, downdraft, cross draft. We have many different systems. Of this, mainly we are used varieties, and we are just showing here. That is updraft gasifier and downdraft gasifier. In fluidized gasifier, of course, we have bubbling, circulating fluidized bed circulator. Then this is going to I have given the capacities also. So this is generally fixed bed is used for low and medium scale heating and power applications. That is from 0.1 to 1 megawatt application range. Whereas bubbling is going to be from 5 to 20 megawatts, and power applications for more than 5 megawatts that demands circulating fluidized bed technology. So now, in our particular presentation, we will be restricting more towards fixed bed gasification systems. And why we are talking about fixed bed gasification is that this is a system which is actually resembling the conventional moving grade boiler, which has been used for combusting the biomasses also in industries as of now. Now, fixed bed technology. updraft and downdraft. I hope I don't want to give more introduction about updraft and downdraft gasification difference here. I will just say air is supplied from here. Oxidation happens in updraft gasifier like this, and whatever the oxidation products which will be at a high temperature that will actually pass through the next zone, that is pyrolysis zone. Whatever the volatiles present here will be getting pyrolyzed here, and the pyrolysis gas also will come along the oxidation products, and this will actually end up to the drying zone where it will dry because of the high sensible enthalpy. It will dry the biomass which is available over here, and this gas will come out here. This is updraft gasification. Whereas in downdraft gasification, we have oxygen entry or air entry here. Now this is getting oxidized. Whatever the volatiles are getting oxidized. Remember, this is gasification. So we only volatiles are getting oxidized. So charge is remaining. The charge is coming down here. This charge, this sensible enthalpy is used to pyrolyze this zone, and this is pyrolyzed, and this will come over here. And now this charge particles will come to the reduction zone, and then this oxidation products will come to the reduction zone, and it will get reduced, and it will form syngas, and we are getting syngas out of here. Okay, the fuel is fed from the top, and air is fed from the sides. This is a typical downdraft system. In fluidized system, we are just having the fuel to be suspended through an air bed, and we are supplying, it's burning overall. It will be having a uniform temperature towards a gasifier, and we will be having the gas out of the system. So depending upon the capacity, it will generally use bubbling fluidized bed or circulating fluidized bed. Okay. Now we will see some interesting facts about biomass thermochemical conversion and what are the very important takeaways from this. Okay. So now, biomass conversion. So biomass conversion can be generally studied. There are a variety of systems to study about biomass gasification or combustion technology or pyrolysis technology. Generally employed technologies are single particle studies, TG or DTA studies, a thermogravimetric analysis or differential thermal analysis study. Differential DT or drop tube reactor studies. We have fixed bed studies, and fixed bed also we can study, and also we have fluidized bed to study. Now here the single particle. So we are subjecting a single particle, we are burning that single particle, we are actually measuring the mass loss of this, and we are actually measuring the temperature gradients across the surface, and we are studying about this is single particle studies. I've just given a snapshot here. The typical heating rates, that is temperature rise per unit time, that is going to be around 1000 degrees Celsius per minute for single particle experiments. Whereas for TG and DTA, it is going to be around 100 degrees Celsius per minute, in the order of 100 degrees Celsius per minute. Whereas in DTR, that is drop tube reactor, that is going to be in the order of 10,000 degrees Celsius per second. Okay, the heating rates are different. Okay, just note this. Fixed bed, again, the heating rates is going to be around 1000 degrees Celsius per minute. Whereas fluidized bed is also going to be in the order of 1000 degrees Celsius per minute. So now we can see the practical gasifiers like fixed bed and fluidized bed that is going to be used in most of the industries. This is having a heating rate which is correspondent to single particle experiments, not with respect to TG or DT experiments or DTR experiments. So whatever the Arrhenius parameters which we are deriving from the experiments which is conducted from here may not be applicable to such practical systems, because this is having a different heating rates altogether. Okay, so I am producing references over here to support this hypothesis, and also my papers also being written in this particular thing which supports this hypothesis. And so that's why we just don't consider TG and DTA analysis, which is actually meant for intrinsic kinetics for Char oxidation reactions, which has been meant for. But remember, biomass is having, as I already said, it has 80% volatiles. Almost 70% of the total heat release is happening because of this volatile oxidation itself, which is going to be a diffusion control process. That is a diffusion control process in the sense this is actually governed by equilibrium, almost like equilibrium. So intrinsic kinetics of volatile oxidation is not relevant to such systems. Okay, so I am not using these things for this particular study. And so for the current study, I can say for fixed bed systems, to study fixed bed systems, a canonical form to, because we know it's updraft gasifier, downdraft, different types of gasifiers, and we are very well aware about the fact that updraft gasifiers generally produce large amount of tar. So downdraft gasifier are the preferred technology which is generally used for power applications. Only for thermal applications or some certain demands, updraft gasifiers are being used, because the tar level and the dust and particulate emissions from the gas and gas obtained from updraft gasifier are generally more. So it requires downstream processing of the gases. Whereas in the down-drop gasifier, that is not the case. So now, when we say, when we take this is a canonical form of down-drop gasifier, which I'm just considering for my study here, which is almost equivalent to study almost like a conventional grate boilers also. I will explain how. Now, I have a fixed bed here and I have a grate here. I'm supplying air from the bottom, and the air is going from here, and I'm igniting the biomass at the top. So now first the volatiles are getting oxidized and they're left with only char. And this, because of this volatile oxidation, the flame is actually radiating toward the next surface. And because the next surface will be now ignited, and the flame front is moving from the top to the bottom as we supply air. Whatever the oxidation products, volatile oxidation products which I get over here, that is getting reduced in the zone here. And the volatile, this reduced syngas will come from the top, which we can take out. So the flame propagates from the top to the bottom as like this. Okay. So this is when you just turn the system upside down, just upside down. This is similar to a down-drop gasification system. Also, when we say, for example, a grate-fired boiler, what is done here is the biomass is fed from here, and the air is fed from the bottom, and the biomass is burnt all the way. And it is when it reaches over this surface, it is almost charred or only ash that is being taken away. So for the flame propagates from the top to the bottom, and air is supplied from the bottom to the top. So the same setup as we study here. So when we study this system, the results can be applicable for down-drop gasification system, practical system, as well as for practically used boilers, biomass boilers, that is, for example, moving rate furnace. So that's why I choose this configuration in particular. I will tell more about this gasification, what is happening in the reactions, or whatever the reaction I will tell later in this next slide. Now, this is why I'm spelling the reason why this is being used as a canonical configuration here. Okay. Now, I will now want to say about an interesting phenomenon, one more interesting phenomenon. So we will be saying in whatever the gasification literature, gasification is not something which is new. Almost like this is a century-old technology. And we take any papers related to biomass gasification, you can see there's a variety of parameters being studied for variety of type of biomass. Okay, they will be studying about the temperature effect, they will be studying about the steam bed to biomass ratio, they will be taking about the equivalence ratio, they will be taking about the oxidizer amount, everything, temperature effect, everything they will be considering. Each parameter wise they will be discussing. Okay, but one important point which is very noticed very later part, only the from Varun Kumar it has been noticed, is irrespective of the composition of the biomass and the variety of the biomass, when we actually speak about a dry and ash-free basis, okay, every biomass exhibit a universal behavior. What I mean yeah. So thing is, when we actually it is only a function of superficial velocity, how much velocity of air which is applied from the bottom. So that actually determines what is the amount of oxidation being fed. That determines the equivalence ratio in turn, which I will explain later. Now, when we increase the oxidizer velocity, that is the air velocity here. When we increase the air velocity, the mass flux, that is the fuel flux, the fuel flow burn rate, or in other words, will actually increase, keep on increasing. And this increasing, there's a linear increase almost. That regime is called as a gasification regime. That is called as regime 1. That is gasification regime. And if you keep on increasing oxidizer velocity, this air velocity here, it will go to a regime called as char oxidation regime. And we still increase the oxidizer flow, that is air flow. What you will be getting is an extinction regime, that is regime 3. So regime 1, steep increase of burn rate. Regime 2, where there is a saturation of burn rate. And regime 3, where the burn rate drops and ultimately the flame extinguishes. That is called as extinction regime. Now, what is happening here? In this regime, the burn rate is increasing because it is gasification regime. So as we increase the air velocity, it will getting more and more of oxidizer to get the volatiles to get oxidized. Since the volatiles are getting oxidized and it is going to be a fast process, the burn rate also increases very steep. But if you just start increasing your oxidizer velocity more, that is, we are going to a regime where we are actually supplying more than 60% of the stoichiometric air here. Now, what happens is char is getting oxidized. So once the char is getting oxidized, when we are going to this regime, the Ash particle is also formed because char is getting oxidized. What is left is only ash. This ash is being covered in the top layer now. For example, this layer is covered with ash. So this entirely covered with ash here. So this actually restricts the heat transfer to the next layer through radiation. So that reduces that. So because of that, what happens? The fuel flux is almost saturated. So it is saturated at this region. And if we still keep on increasing the air velocity, so that actually what happens is because of the convection cooling, the biomass surface is getting cooled, and because of that cooling, it is getting extinguished. There is no flame propagation at this particular regime. Okay, so this is very important point. This behavior is called as universal behavior, and this is universal for all the different types of biomass. You can see the variety of biomass have been studied here. You can see here. For all the biomass, this is common, and almost this fuel flux is also for air as oxidizer. This is also common, like it is from 30 to 80 grams per meter square per second. Okay, so this is a value. This is one important observation. And one more thing is volatile oxidation is diffusion control. So that means whenever the oxidizer comes and meets the volatiles, it is completely burnt. Okay, the time which limits this conversion process is only the diffusion time, not the chemical kinetic time. So chemical kinetics is of less relevance in these systems. So that is an important takeaway. That has been proved by here, where there is a oxygen drop exactly at this flame front for different velocities, which has been tried over here. That has been shown. Now, heat balance for this is a universal propagation model. So based on which now I just said. So whatever the total time required for the biomass to rise from ambient temperature to TP is called as the temperature of the particle. When the temperature of the particle reaches the ignition temperature of the particular biomass, it gets ignited. That's where we call there is a flame. So the rate of change of increase of temperature in a particular time, rate of change implies it's a time. So rate of change of increase of temperature from ambient temperature to the ignition temperature is actually a function of what is the total amount of radiative energy which has been given to the surface of the particle to the convective loss that has been modeled. And based on this, if this generally this Ts is the surface temperature and Tp is actually the particle temperature, the initial particle temperature. This term is actually very high when compared to this term, so this has been dropped. So this entire equation is actually integrated from T0 to Tp, and that time is called as ignition time. So R dot is nothing but propagation rate, which is actually D is the diameter of the particle. And for the diameter of the particle, that what total time for the ignition is T ignition, and this has been given by this function. And there is a detailed model available in Varun Kumar et al. Which you guys can go through. So here it says that it is actually this particular model says the propagation rate of a biomass in a packed bed reactor is going to be driven by ignition time, the time taken for the biomass to raise this temperature from ambient temperatures to the ignition temperature. So that is a takeaway here. Okay. Now, based on this model, this model actually works well with, this is the experimental results, and this is actually the model result. It matched very well with the experiments, the UFP model here, and it has been called universal propagation model, flame propagation model. And we can see here, when the velocity is going to be 7 centimeters per second, this is going to be gasification regime. Whereas when it goes to 20 centimeters per second, there is simultaneous char and volatile oxidation taking place on the surface. Whereas here, it is in a staged manner. Char is getting reduced here, volatile oxidation is happening here, then this is the fresh layer of biomass. Whereas when we increase the velocity, when we go to char oxidation, all is happening in a single layer. We can see a single orange line. That has been shown in the figure also, which is actually an experiment takes from a transparent quartz reactor. Okay. So now, having said this brief, so we should be able to analyze these points. Having said that biomass exhibits universal flame propagation behavior, the parametric studies, for example, temperature, biomass types, equivalence ratios, steam to biomass region, are they really relevant? They are not completely not relevant. They are relevant. But is there any unifying parameter to analyze this all above in a single unifying parameter? Maybe preferably a non-dimensional parameter? That is one thing which you have to consider here. And will the biomass flame propagation will be still universal if we use oxidizer, which is other than air? That is one more question to be answered. Or what will happen to the flame propagation? Whether it will be steady or unsteady, something may happen. What will be the answer? That is one thing. One more thing. And if the UFP model is, whether the UFP model, whatever we have seen before, just before, is self-contained for all the fuel oxidizer combinations, or it is going, or for all the operating conditions. That is the question which you have to answer. So now, based on these questions, I'll go to the new findings, which is from my experimental results and from my theoretical analysis. I'll go to this now. Now, a typical downdraft gasifier. Okay, we are getting a syngas and we are using this syngas. We are actually powering an IC engine, and from IC engine we are producing power. Okay, typical downdraft gasifier engine. There are many established technologies for this. One example, say for example, IAC based downdraft gasification system, open top downdraft gasification system is one example for this. Okay, now generally the syngas which is out of this downdraft gasification contains more than 54% of nitrogen inert, because we are using air as a gasification medium. Okay, so because of this, the calorific value of this particular syngas is going to be very low. Correct? It will be only 4.5 megajoules per meter cube. So now, if at all we can replace this nitrogen with some reactive components like O2 CO2 or mixture of O2 CO2, mixture of O2 steam or mixture of O2 CO2 steam, whether we can able to do some, we can able to get some medium calorific value is something which we have to try. Whether it will also enhance the fuel flux, that is a burn rate from 50 to 70 grams per meter square second, whether it can enhance further also, that is something which you have to study. This is also should be economic, energy friendly and eco friendly. Okay, both manner it should be friendly. Now I'll explain the thermochemical conversion of a biomass in a packed bed gasification system. As I now I have given all enough introduction. Now I think you can able to understand this slide very better. Now I am having a packed bed of biomass and I am supplying air from the bottom or any oxidizer for this case from the bottom, and I am supplying air which is lesser than or equal to 60% of the stoichiometry. So this is going to be gasification for sure. Now I am igniting the flame at the top. Now once it is getting ignited, the first layer will be oxidized, volatiles will be oxidized, and the layer formed is going to be char. After char is getting formed, the next layer is getting ignited, the next layer is getting ignited, and that is volatile oxidation now taking place in the next layer. Orange layer is actually volatile oxidation. This is char, which is left behind. Now, this volatile, this is devolatilization, and this is char layer, which I already explained. And now, whatever the volatile is getting oxidized product, that is fed to the char layer now, and we are getting this products as a syngas composition. So these are the typical temperatures in each and every layer. Char layer is typically 200 to 500 degrees Celsius lesser than the devolatilization layer. And this is devolatilization, which is actually combustion layer, which is actually having a maximum temperature. And then we have fresh biomass to be here. So this is gasification. So we will see a little detail here, the same figure. So biomass subjected to heat, air as a gasification medium. We are forming CO, CO2V, H2, H2OV, CH4, HSC, and this is a volatile oxidation products. So CO2V, that means CO2 released from volatile oxidation of volatile hydrocarbons. So that is CO2V. Similarly, steam, H2OV, that is volatile H2, volatile H2O, volatile carbon dioxide. That is an important term here. And this is now getting reduced with char, that is carbon. Simply you take as carbon as of now. This carbon, what are the main major reactions are this? C plus CO2 gives 2CO, Baudegard reaction. C plus H2O gives CO plus H2, this char steam reaction. CO plus H2O gives CO2 plus H2, this is water gas shift reaction. So these reactions takes place here in this region, and we'll be getting a syngas. Sorry. So we'll be getting syngas. So that is what we taught. So this is what we discussed. Now I'm using, instead of air, I'm using O2, CO2 or steam as an oxidizer here. So in addition to air, I am replacing air with O2, mixture of O2 and CO2 or O2 and steam here. So what is, in addition to volatile CO2 here, in addition to volatile CO2 and volatile steam, I'm having additional steam and CO2 here. So there is a possibility of this steam and this CO2 may get converted with this char fully, and I can get enhanced CO and H2. That is the idea. Sorry. So that is the idea. So from this I can able to get what is the net CO2 conversion. So for that I should know what is the total mass of volatile CO2 and what is the total mass of volatile which has been fed here, and what is the total mass of CO2 which is coming out of my system. From that, when I divide per unit of kg of biomass which has been loaded in the reactor, I can able to get what is the net carbon dioxide conversion I can able to find out. From this, actually, same thing can be done for steam also. From this, for air cases, these two parameters will be 0. this will be 0, and this will be 0. So this is meant for CO2 reduction. We are reducing CO2 to some useful product, that is carbon monoxide, and here we are actually easily reducing this steam to hydrogen. So that is what being done here. So this is my thesis work. I'll just go through very fast because the time is less here. So I'm using this. As I already said, TGA-DT has not been used. Fluidized bed is not been used here. Fixed bed has been used. Updraft is not used because it is actually having a lot of tar content in the gases. And now we have downdraft gasification system. In downdraft gasification system, people have done this research, and mainly the volatile CO2 has not been accounted for, and I have done that. And for a O2 steam mixtures, people have generally have an habit of get more hydrogen. People, what they usually do is they operate on a very rich regime. So whatever they get is actually volatile H2, which they get. Volatile H2, what I mean is the hydrogen is released because of this volatile decomposition. That is what they get. And because of this rich operation, what is happening is they are having a high tar in their product. So what I am trying to do is actually what I did was actually I replaced this mixture with the O2 and steam. I am operated this is a slightly rich mixture, not very rich, slightly rich, and actually I can able to get more H2. Similar, it's the same HCMs2 as that of they get in rich operation. So this is what I have did. So these are the objectives of my current study. I'm just skipping this section as of now. I'll explain the results directly now. So this is the experimental setup. So I have a reactor, and I supply air from the bottom. I have temperatures over here, and from this flame, I take the syngas samples. It's getting cooled, it is filtered, and then it is fed to the gas chromatography. And then from this entire reactor is being mounted on a weighing balance, so that I can able to get the mass loss rate, and also also I measure the temperature with respect to time. So these are the things. So what are the different oxidizers I use? Is air I use, mixture of O2 and N2. Mixture of O2 and CO2, mixture of O2 and steam I use. So based on this, actually I have different varieties of combinations. From here I am operating from a very rich operation to Chow oxidation. Entire regime has been studied for each and every experiment. Almost like more than 100 or 120 experiments have been carried out in this particular thing. And now these are the main outputs. So what is the mass loss rate with respect to time? What is the temperature with respect to time? And what is the gas composition from the bags, whatever we are sampling from gas chromatography. That is a syngas composition. So now the algorithm to calculate. So I know what is the biomass which is being loaded in my reactor. Now I know what is the total reactant. So from the end of the reaction, I know only the fixed carbon and ash will be left because this is gasification. So what is that I know? Now I know what is the total amount of oxidizer which I have been fed to the system, and from that I can able to calculate what is the total reactant mass. Now, from the ultimate and proximate analysis, I can able to find what is the CHO content of the total reactants. Similarly, from the syngas output, that is from the gas chromatography output, I know the gas composition by mass. Now, that is dry products. Now, I am assuming some wetness there because I am actually taking the moisture, I am filtering out the moisture, and then only I can able to sample in the gas chromatograph. Now, I am assuming some wetness fraction. And with this wetness fraction, I'm calculating the CHO balance, and the CHO balance between the reactants and product should be less than 10%. So that is my criteria for convergence. Now, if it is not converging, then again go to the thing and assume a different wetness fraction. So this is an iterative process. Still there is a mass loss which is actually where the CHO mass balance is less than 10%. So from that I can able to get what is the total mass of CO, CO2, H2, everything I can able to get from this. Okay. Similarly, I said volatile oxidation is diffusion control. That means I can do equilibrium calculations for volatile oxidation products. I can calculate the CHO of the volatiles. I can actually use NASA CEA equilibration software, which is available, freeware available, and I can actually compute what is the total mass of oxidation products from this oxidation products. And from this oxidation products, the difference between this MCO from here to MCO will give that net CO yield. Similarly, CO2 from here to CO2 from here will get the net CO2 conversion. So like this, I can able to calculate my things. So this procedure is also done for energy balance, also being done. So it is being ensured that the elemental and we are enforcing elemental mass and energy balances to compute this net carbon dioxide conversion and net steam conversion and so on. Now, I'll just brief some important results. So as I said, I'm increasing what I'm doing in my experiments are actually I'm increasing the oxidizer mass flow. So that means I am increasing the equivalence. I am decreasing the equivalence ratio. Okay. So as I go decreasing equivalence ratio, PV is 1. That means volatile stoichiometry. That is, if the PV is greater than 1, that is rich conversion. When PV is less than 1, that is char oxidation. That is combustion part. So when PV is more than 1, that is gasification. Now, for different cases, that is PA. PA means pellet. I use different fuels. PA means pellet air gasification. P25C means pellets with 25% of carbon dioxide and remaining 75% is going to be, P25C means 25% is oxygen and remaining 75 is going to be carbon dioxide. It's the same case. It goes like this. We can see the net carbon conversion, the next net carbon dioxide conversion, the net CO2 conversion is almost maximum for all the cases, air cases, at around PV of 1. That is, at volatile stoichiometry, that is what we get. So exactly at volatile stoichiometry, we can see the peak bed temperatures here. The peak bed temperature is almost 1500. So the peak bed temperature is increasing. So that particular thing, remember, whatever the volatile oxidation products from volatile, that is a volatile CO2 which is present in the oxidation product, it is now attaining a temperature of 1500 degrees Celsius. So this is reacting with the char. So this char is getting converted to CO. So there is a net carbon dioxide conversion there. So this happens only when the PV is reaching towards 1, not below that. Okay, so that is a very important point here. So that is what I have given here. As MOX increases and reaches towards PV equal to 1, TPB increases beyond 1500 kelvins, favoring border guard and water gas shift reaction, favoring NCC. NCC is net carbon dioxide conversion. So around 200 to 300 grams of CO2 is getting converted per kg of biomass which has been loaded. Okay, so CO yield is around 200 to 400 grams per kg of biomass with air cases. Okay, now the char conversion is also 100% below before this char oxidation. That means it is not char is not participating in oxidation. It is only participating in reduction reactions. That is an important takeaway here. So now, if you take carbon dioxide cases, now if, for example, you can see here, this case, for example, there is this pentagon. This pentagon is P30C. That means 30% is oxygen, pellet case, remaining 70 is carbon dioxide. Okay. Now here we can see almost like PV equivalent to 1. That is P0.96. We can see the net carbon dioxide conversion is almost 600 grams. Whereas for air cases, it is going to be 200 to 300 grams. Here is almost double. Okay. And similarly, since this is double, CO yield also will be double. Okay. Because of the increased CO yield, we can see for air case, the gasification efficiency for the corresponding point is only 43%. Whereas for the same thing, if the corresponding point over here is going to be around 85% is going to be the cold gas efficiency. That is almost happening on volatile stoichiometry. So this is the percentage cold gas gasification efficiency improvement because of using CO2 in particular at volatile stoichiometry, not before. You can see before that you don't have increased cold gas efficiency. Only here you can find increased cold gas efficiency. Okay. So because of this, we can have enhanced CO in the syngas. Okay. Now, okay. So also the fuel flux. Earlier, I showed a universal propagation plot where I used air as a gasification medium. Now I'm using different oxidizer combinations, which I discussed in the earlier slides. So I'm using different oxidizer combinations. I can see when I plot with mass of oxidizer flux to the fuel flux, it is different numbers or different cases. It is very high. It is more than, it is almost reaching 250 also grams per meter, which is almost like 3 or 4 times higher than the conventional air gasification mode. Okay, so but we can see when this is all happens when there is an unsteady propagation, whereas in steady propagation regime, this can be actually unified into a global formula where the volatile heat release rate is going to be higher when the oxidation fraction is going. When the oxygen fraction is high in the oxidizer, that enhances the heat release rate of the volatile oxidation. So because of that enhanced volatile heat release rate, this actually causes a very high fuel flux in the reactor. So that is being modified using this correction factor, and we can see that modified normalized fuel flux is going to be again going at universal flame propagation behavior here. Okay, so this is a thing, something which I have done here. And so all the propagations regime are not steady. When we actually go for steady propagation regime, a steady propagation plot will something look like this. We can see the thermocouples rising to a peak temperature at a regular time intervals, almost regular time intervals. The thermocouples here, when the flame front reaches here, it reaches the peak bed temperature. So this will be almost this uniform. The intervals will be almost uniform. But this is not the case with all the types of fuel sizes, biomass fuel. When the biomass fuel particle size is increasing, so what happens is the time of the total. So far we have seen from universal propagation model that ignition time is what important. So once the biomass is getting ignited, the time for it to get ignited is actually more or comparable to the total devolatilization time of the biomass. Devolatilization time of the biomass is nothing but the time required for the biomass to completely release its volatiles. So that time is comparable for small size particles. Whereas when we go for large size particles, what happens is the time the biomass is getting ignited to the next layer, but still the previous layer is not completely devolatilized. So there is a gap here. So because of that, what happens? This conversion will happen on the whole. So because of this, what happens? The fuel flux actually reduces. That is one phenomenon of flame jump, what we call it. The another one predominant that is not very severe as the second case, what I'm now going to discuss, because when we increase oxygen fractions, as I already said, this when we increase oxygen fraction, the volatile heat release rate is going to be very, very high. So because of very, very high volatile heat release rate, what happens is that the flame jumps from one layer to another layer very, very, very soon, before even devolatilizing the previous layer. So because of that, what happens is that the flame jumps. For example, you can see the flame propagation is very steady here. Whereas when we can see a case of this, whereas the oxygen fraction is almost 50% is the oxygen fraction, and the remaining is CO2. For example, there's a coconut shell case. Here, we can see that at the same time, all the thermocouples are reaching some peak bed temperatures, and it is actually moving in a random fashion here. So this is called as flame jump. So there are two cases when we increase the particle size diameter. When it increases beyond 20 mm, equivalent spherical diameter of the particle, we have devolatilization time and ignition time to be not comparable. So this is one flame jump phenomenon. And another flame jump phenomenon another flame jump phenomenon is when the oxygen fraction is increasing. So this is one more. So this is what we are saying. So based on this, I have actually developed a model from first principles using classical droplet combustion theory, invoking transient heat conduction equation subjected to boundary conditions. I computed the ignition time and devolatilization time for the biomass when it's subject to different flux conditions. So based on this, I have plotted here, and this plot shows I can mass loss rate with respect to time for a single biomass particle, and this is going to be matching with a single biomass experiment also. There's a very good match here. Similarly, the model that model is called as unified ignition devolatilization model, which is developed and I've discussed in the my papers. And when we go for the other things, similarly, when the particle size is increasing, the ignition time and devolatilization time become uncomparable. So that is also being captured from this experiment, from this model results. And we can see when the oxygen fraction increasing, also the ignition time actually drops, and the devolatilization time actually also drops, but not as like ignition times. And there is a gap between ignition time and devolatilization. There is a clear gap. So based on this, there is a regime map which I formed. So now, instead of saying various parameters for gasification like equivalence ratio, temperature, steam to biomass ratio, and all those things, I am just capturing one parameter, that is volatile equivalence ratio, that is PV, non-dimensional parameter. This is plotted against TV by T ignition. That is the total time for volatilization by ignition time. So when there are conditions like ignition time is comparable to devolatilization time, this number will be almost equivalent to 1 or lesser than 1 also. That time the propagation is steady. So when the number TV by T ignition is increasing at higher oxygen fractions because of the volatile heat release rate increase, what happens is there is a possibility for flame jump. Okay, so this is the takeaway. So now based on this, I have given this regime map. I can see I have for all the cases which I have done the experiments, I have plotted the cases over here, and we can see here the TV by T ignition is plotted against PV. So the non-dimensional graph here. So no additional parameters. Of course, PV actually a unifying parameter which actually captures all those behaviors also. So now we can see there are mainly 5 regimes here. Zone 1, that is here, okay, where we have TV lesser than TV by T ignition lesser than 0.75. That means here in this regime, the ignition time is actually more when compared to devolation time. So that means the propagation will be slow and steady. It will be there. Okay, so that is one regime. Second regime is where this ratio is between 0.75 to 2, and PV is going to be between 2 to 1. So in this regime, what happens is, earlier it was a rich regime. Here it is actually fuel rich. Here it is going to be so this PV is not applicable here. Only there's a dash here. Sorry. And when zone 2 is going to be here, it is this TV by T ignition is 0.75 to 2, and the PV value is between 2 to 1. Now in this place, the PV is from 2 to 1. Almost near to the volatile stoichiometric region. That means higher temperatures, higher conversion of CO2. Similarly, for steam also it will be higher conversion there. Okay, so we can get more CO and hydrogen in the syngas as compared to the earlier cases. Whereas when we operate in zone 3, that means TV by T ignition actually is greater than 0.75 to 5. That means it is actually a region where it is about to do flame jump and it is rich. So the char conversion is not complete here. There is zone 4, that is where this TV by T ignition is 2 to 5. That means it is in a flame jump zone. This is unsteady operation. So where this UFV models cannot able to predict the behavior here. Okay, only the UFV model can predict the behavior only over here. So that has been captured from UID model. And then we have zone 5 where it is a star oxidation region, where we have PV is lesser than 1. That is star oxidation. There is no gasification there. Okay, so these are the important takeaways from my work. Okay. And this is related to hydrogen experiments. As I already said, I'm skipping these slides. But the only important takeaway from this hydrogen is that the intrinsic hydrogen yield, that is from the intrinsic means I am not supplying any high temperature steam. I am generally supplying steam in the range of 120 degrees Celsius to 150 degrees Celsius as a steam temperature. And with this steam temperature, I am able to achieve hydrogen yield as compared to hydrogen yield obtained from the previous researchers with very high steam temperatures or very high fuel rich operations. I am getting the same hydrogen yield, comparable hydrogen yield from my experiments with when operating to volatile stoichiometry. So that is an important takeaway from this work that has been explained over here. So because of this, what happens is, since I am operating near volatile stoichiometry, the tar component of the gas is going to be very less. And because of that, there is a tar-free syngas which is rich in hydrogen. So that is an important advantage of using hydrogen for generating hydrogen at volatile stoichiometry. So that has been brought away here, which has not been brought about in earlier literatures. So char conversion also is about volatile oxidation. So that means char is participating only in reduction reactions. So we can see hydrogen yield is almost constant, and it is almost 2 to 2.5 times higher than that of the conventional air gasification. So this is a summary. Fundamental studies of flame propagation of fact bed countercurrent reactor in both gasification and conversion regimes are explored with O2, CO2 as well as O2 and steam mixtures. Conversion of CO2 to CO and steam to hydrogen are quantified. But it's quantified here. That is the important thing. It has been quantified by a new procedure invoking volatile equilibration and enforcing elemental energy balance, which is first of this kind. And presence of CO2 in the inlet stream promotes char reduction reactions. When the operation regime shifts near volatile stoichiometry, the peak bed temperature is actually rising above 1500 degree kelvins, and significant net carbon dioxide conversion is observed. Maximum net carbon dioxide conversion of 627 grams per kg of biomass is observed, which is almost 2 to 2.5 times higher than the corresponding air case. Also, using a UID model, a map showing distinct flame propagation zones of biomass is being presented, and this is can be directly used by practitioners to design their gasification systems with O2 CO2 mixture or whatever oxidation they want. And with that, with oxy-steam experiments, the intrinsic hydrogen yields is also been measured and it has been calculated. And with both O2 CO2 and O2 oxy-steam cases, the exit gas contains only the gases like CO, H2, CO2 and methane. That means it's very easy to separate CO2 from this, and we can easily sequester the CO2 also very easily. Okay, that is one main important of using O2 CO2 as oxidizers. Okay, now what are the important takeaways? So first thing is, irrespective of the biomass type and fuel flux, the fuel flux almost remains constant from 30 to 80. This is true for even other oxidizer when it is going to be operated on steady propagation regimes, not on flame jump regimes. Now, knowing this, we can actually, this is not going to vary with different biomass also. So that is a very important takeaway. Okay, irrespective of the oxidizer, in a fixed bed gasification system, the fuel flux is going to be remaining constant. That is one first important takeaway. The practical design parameters of operating any biomass combustion system like burn rate, net CO2 conversion potential, and hydrogen yield can be computed without any complex chemical kinetics being involved. Of course, chemical kinetics is important when we actually wanted to compute the chemical composition of the syngas or emission predictions where chemical kinetics has been involved. But here, in this case, if at all we wanted to, if you want to calculate the burn rate, we need not use chemical kinetics. We just wanted, with this procedure of volatile oxidation, invoking volatile equilibration and invoking elemental and mass energy balances, we can actually compute the net CO2 conversion itself. So there is one more important takeaway. Instead of concentrating on the power of heating applications, research should be more focused on instead of using biomass technologies for power and heating applications, we can actually focus our research by using mixtures of O2 and CO2 or O2 and steam or a combination of all these things to produce fuels and chemicals or some other value-added products like biochar or some activated carbon. We can use this for this purposes. That is the thing which we can do further, because all the other things are almost answered and remains irrelevant for the community anymore, in my opinion. And third and last important takeaway is, now we can ask, air is free but O2 is not free. Of course it's not free, but the recent advancements of O2 separation technologies like cryogenic air separation, membrane technologies are actually evolving, more and more evolving, and for even with the costliest cryogenic air separation technology, for a decent scale of 5 megawatt electrical operation, even with well-matured technology like cryogenic air separation, the energy consumption is only about 6 to 10%. So this may actually even further go down with the advancement of separation technologies, which is coming in near future. So this will actually be very, very economical in near future too. So these are my references. Thank you. I'm open for any questions. Thank you.
Sir, thank you, sir. It was really a good presentation, and we are getting many positive feedbacks from the participants also. Really, thank you for this. We have a few questions from the participants, sir. Shall I discuss that question with you?
Yeah, sure. We can go over this.
Okay. Sir, the first question is from Abhishek Nayak, and he has asked how biogas plant can be cost effective. Can we use synthetic fibers instead of metallic plants and produce biomass plants?
Sorry, is the question is about biogas?
The question is about how to be cost effective.
Which technology?
He has asked, can we use synthetic fibers instead of metallic plants and concretes to produce biogas plants?
Not understanding the question actually. Actually, the question is not understandable to me. Biogas
Okay.
technology is something like that is with respect to some biodegradable components only we can use. Synthetic fibers, I don't know. I'm not getting the question. Sorry, that is the question is not understandable to me.
Okay, fine, sir. Another question from Manjunath. Uh, the question is it possible to produce biogas from meat?
Yeah, it is
And what
possible.
would be the cost to install a biogas plant for a member of 3 family members?
This presentation, actually, I am not from the area of exploitation of biogas synthesis. That is actually biomethanization process. Actually,
Okay.
I am with the thermochemical conversion only. I am working about biogas. Of course, there is an answer is yes. For meat, we can actually use that. But meat, I should be very clear whether it is meat or meat waste. I don't know that because with that we should actually estimate the total volatile. I will tell what is the procedure. That's what I can tell now. I don't know the exact numbers. With the
Okay,
wheat
sir.
meat, we should actually calculate the volatile content of that particular biomass. That is the wet biomass. Each and every volatile matter content will be capable of producing certain meter cube of methane plus CO2 gas. Based on that, we should able to based on the conception of the unit home, we should actually calculate that number. But I am not sure about that numbers because I am away from that field. I am not into that field. Sorry, but this is
Yes,
a
yes, we
procedure
can
what they
understand.
do.
Okay. Okay, thank you for the explanation, sir. One more question from Joe Patrick, sir. The question is, what is the scope of recycled plastic waste for energy generation or biomass gasification?
Sure. Yeah, very valid question. Actually, recycled plastic waste also can be used because when we take recycled plastic waste, we can actually have that recycled plastic waste is nothing but a thing which is actually having no char. There is no fixed carbon as such. Okay, everything is actually mostly it is volatiles. So what we can do is so volatiles is actually used to enhance the propagation rate. So what we can do is we can actually have a good fraction of volatiles and we can actually good fraction of this bioplastics and some biomass also put together, and this put together we can actually use in a gasifier and we can actually produce some more power or more power or fuel or chemicals. This can be done. And also there are projects which has been running around with purely with bioplastics, with plastic waste also to produce directly chemicals. That is also possible.
Yes, thank you, sir. One more question from Makeshwari, madam. The question is, what is the difference between biomass gasification and pyrolysis?
Biomass gasification, pyrolysis. Okay.
Yes, what is it?
As I already said, biomass gasification means we are supplying, if you supply 100% stoichiometric air required for the complete combustion, that is biomass combustion systems. Okay, what we will be getting generally is if it is complete combustion, carbon and hydrogen will be oxidized to only carbon dioxide and water vapor. But in gasification, what we are doing is we are only supplying 60% of the stoichiometric air, or even lesser than that. Lesser than that, it can be any number. Now, if it is something around, say, for example, 30% of the stoichiometric air we are supplying. So what happens here is the volatiles are partially oxidized. Partially oxidized means it will be containing a mixture of CO, CO2, H2O, H2, methane, everything will be present in the gas. Now, this gas will go to the next layer of char, or even some volatiles also, if you have it's very rich means even volatiles are being left without conversion. Now that will react with those and it will actually produce more CO2 will be converted to CO, H2O will be converted to H2, and methane will be converted to higher hydrocarbons, and some methane will be formed. That is the complex reaction which take place. But if at all you are supplying exactly 60% of stoichiometric, for example, we say we are supplying 60% of stoichiometric air, that means the volatiles are completely oxidized. The carbon and hydrogen present in the volatiles of the biomass is completely converted to CO2 and H2. This CO2 and H2O is now given to char, that is nothing but simply carbon. C plus CO2 can give 2CO. C plus H2O can give CO plus H2. So because of this, there is an enhanced formation of CO and H2 in the syngas. So this is gasification. When we go to pyrolysis, we have no oxidizer at all. For example, it is zero. That means we are just heating the material. That means whatever the volatiles which I said, that is carbon and hydrogen which is present there, that gases will start to evolve. That gases are nothing but higher molecular weight hydrocarbons which will start to evolve, which will eventually condense. That means there are low evaporating hydrocarbons. It will, once it is getting evaporated, it will, when you just cool it, it will immediately form into some liquids. That is what pyrolysis is all about. It is just a thermal degradation of biomass. That's why I said thermal degradation. We are just eating it. The volatiles are evolved. We can just see a classical example when we use wood in a conventional three stove, what we use in villages. You can see always there is a liquid which is oozing out from the wood. That liquid is nothing but pyrolysis oil, which is nothing but the evaporated volatiles are getting condensed there since it is contact with the atmosphere and it is forming a liquid. That is pyrolysis oil. That is what we exactly do in pyrolysis also. We will supply either lesser than 10% of the stoichiometry we will supply, or we will not supply anything. We will just simply give external heat source and that will be formed as an oil. Oil and char will be left out. That is pyrolysis. Thank you.
Thank you very much, sir. One more question from Saravana Kumar, sir. The question is, which kind of metal catalyst is best suitable hydrogen protection for biomass gasification?
Which kind of metal?
Metal catalyst is best suitable for hydrogen protection in biomass gasification.
Yeah, actually, most commonly used catalyst is actually nickel catalyst is being used. There are iron catalysts also being used for Fischer-Tropsch synthesis, and also some reverse water gas shift reaction is also being used as a catalyst to enhance the hydrogen production currently. There are many other catalysts available also, but ferrous catalyst and nickel-based catalysts are something which is well known for very long amount of time.
Okay, thank you, sir. One last question, sir. The question is how to calculate the efficiency in biomass plant?
Simply, you know the syngas has been generated and you know the composition of the syngas. So from that syngas composition, you can actually calculate the calorific value of the syngas. So that is a total output from the system. And also there is one more system. There is two type of efficiency. One is hot gas efficiency and one is cold gas efficiency. So hot gas efficiency is nothing but when the syngas is coming out of the gasifier, it is going to be already at a higher temperature. So if you account for the temperature also, there is a sensible enthalpy there. If you take that sensible enthalpy plus this calorific value put together, then it is called as hot gas efficiency, which is going to be higher. Whereas when we cool the syngas, and we take only the calorific value of the syngas divided by the total calorific of the value of the biomass itself, that gives the cold gas efficiency. So that is a method to estimate the efficiency of a gasification plant.
Thank you, sir. That's all about it. We have some more questions also, sir. But if the participants are really interested in taking this topic as their research, we will be directing them to contact you directly, sir.
Yeah, sure. And also people can, whoever can't able to ask these questions right now, can actually please email me. My mail ID is given here. You can just email at any time and we can discuss, no problem. Thank you.
Thank you, sir. It was really a wonderful experience in discussing this topic with you, sir. Thank you.
Thanks for your patient listening.
Thanks a lot.
Thanks for your patient listening too. Thank you.
My greetings to all of you. I feel honored and privileged in getting this opportunity to propose the vote of thanks on this special occasion. First and foremost, I thank the Almighty for making this event possible. On behalf of FXEC, I would like to extend my sincere gratitude to the Honorable Speaker Dr. V.M. Jagannathan, Assistant Professor, Department of Energy and Environment, National Institute of Technology, Tiruchi, for accepting our invitation and delivering such an informative lecture on biomass gasification, facts and future research. We have professors, research scholars and UG and PG students as participants. Surely this session will help them to explore new avenues of research in the domain of biomass gasification. I extend my heartfelt thanks to the management, respected General Manager Development Dr. K. Jayakumar sir and our beloved Principal Dr. V. Velmurugan sir for their moral support and tremendous guidance in conducting such a productive program. Finally, I would like to place on record my sincere gratitude to Dr. Joe Patrick sir, the head of the department, Dr. Jinatul Farida ma'am, Dr. I. Nidhi Manikam sir, Mr. Sheikh Sulaiman sir, Mr. Ramkumar sir, and all our colleagues. Without their help and guidance, the program would not have been a grand success. Special thanks to our student Mr. Jason for his support on web screening. This webinar was made successful only because of well-wishers, followers, and participants of this event. Once again, thank one and all. Stay home, stay safe.